Okay, so your quiz is graded. I am looking through it again. I will probably bring it back to you on Monday. So I just got them today, so I'm reviewing them. And next week, there's no actual lab. However, on Wednesday, there is a review session in lab. So you come to the lab on Wednesday, don't come on Monday if you're a Monday group. We're going to go over questions that will potentially appear on the final. So you want to be there. I can go over any questions that you guys have. We'll go over practice questions, and many of them will be on the final. So you don't want to miss the review session. I will not record it. So please do come. I will try to finish some of lecture material during the review session too, because there is a potluck happening. How's it going, Isaac?
I think we have 8 people, maybe 10.
Maybe 10. Great. I'll bring something. I didn't sign up for anything. It'll be a surprise. Whatever I can make, I'll bring. So yeah, so I'll see you in the review session. Please be there for your own benefit. Again, remember Monday lab. There's no Monday lab. Monday lab people will come to the Wednesday lab. We'll meet in the lab for that lab period. We'll have today's lecture Monday and Wednesday's lecture potentially short with lunch. Okay. What else do I have for you? I guess this is it. Okay. So new topic, use of enzymes in food analysis. So I have few examples. What's happening? What's happening? No, I don't want that. Okay. All right then. Okay, so do you know what enzyme is used to keep the sugar in a liquid and not crystallize? So here you'll have a cherry coated with chocolate, and the syrup over storage, if we just use sucrose, it will crystallize. Do you know what they use? Not pectinate, you have sugar, right? So you want to convert sucrose to something that will not crystallize, and when you bite into your cherry, you still have that juicy syrup rather than a crystallized syrup. Kevin?
Isomerase.
Isomerase. Well, isomerase, you use here. I'll get back to isomerase. Invertase. So you use invertase, is also known as sucrase, easier to remember. It's going to break the sucrose into glucose and fructose. You will actually get higher sweetness because fructose is sweeter than sucrose, and you will have longer time before crystallization. Sucrose crystallizes much faster than fructose and glucose. So here, corn. Why do I have corn here? What do we get out of corn that is sweet? High fructose corn syrup. So we take the starch, we break it down into glucose. What do we use to break the starch into glucose? Try to remember from your carbohydrate lecture. What enzymes are used to break down starch into glucose? All of this is good for the final, you guys, to remember. Sam.
Glucoamylase.
Glucoamylase. Before that, what we do is we break it with alpha amylase to break it down into smaller maltodextrin chains, and then glucoamylase will break each glucose at a time. But it's high fructose corn syrup, not high glucose corn syrup. Isomerase. And then we use the isomerase to convert glucose to fructose. So these are two applications. When we pour orange juice, if we buy the orange juice that has pulp, when you pour your orange juice, you want the pulp to stay and you don't want it to sediment. What enzyme do we have to inhibit to prevent sedimentation of your pulp? No? Okay. Pectin methyl esterase. So pectin methyl esterase, the pectin, part of the glucuronic acids are methylated. Pectin methyl esterase is going to break down the ester, and it will enhance the formation of, if you have divalent ions in there, it's going to form, with divalent ions, going to form bridges with the pectin, and the pectin will precipitate, the pulp will precipitate. So when you process your orange juice, you want to inhibit pectin methyl esterase. What else do I have here? I have flour. So have you heard of something called falling number? Probably not. Okay, so it's a common test for flour to determine whether or not you're going to be able to build viscosity. Alpha amylase is an endogenous enzyme in flour. And if it's very active, what's going to do is going to chop up your starch. And then when you add water to your flour, you won't form as much viscosity. So the way it is measured, the alpha amylase activity, indirectly, you get the flour, you put it in a graduated cylinder, you put water, and then you put something like a plunger, and then you measure the time it takes for the plunger to drop. The faster the plunger drops, that means you have less viscosity, you mean have more endogenous alpha amylase, so which is impact the quality of your flour. You don't want to have high alpha amylase activity in your flour. So enzymes are important, basically. These are just few examples, and we're going to talk about other examples. So importance of enzymes in food systems. Have you heard of alkaline phosphatase enzyme in milk? What do you guys study in processing? I don't know what you guys cover. So how do you test the efficiency of pasteurization of milk? I'm not blaming you. I'm going to blame whoever is teaching you different classes. Okay, I'm not shaming any of you, you guys. You're here to learn. So alkaline phosphatase is a very important enzyme in milk. So what happens is when you pasteurize milk, you are actually trying to kill all your pathogens, right? We know this much from pasteurization definition. Killing all the pathogens. Very good. But to determine whether or not pasteurization happened and all the pathogens are killed, you have to do a microtest. How long does a microtest take? 2 days, maybe? Okay, you have to test, incubate, plug, get the result. We don't have that for quality assessment. We don't have that much time. So what they often do is measure the activity of alkaline phosphatase enzyme, which is a thermally stable enzyme. If it's inactivated, that means all of your pathogens have been killed because it's more thermally stable than all the pathogens. So pasteurization is checked in milk by measuring alkaline phosphatase. All right, so what else can you give example? How do you test efficiency of blanching? Do you know what blanching is? What does it do, Braden?
I know it deactivates the enzymes.
Absolutely. It deactivates the enzymes because if you want to freeze your vegetables or you want to process them, store them, you don't want enzymes like polyphenol oxidase to cause browning, for example. So you blanch to get rid of the enzymes. Do you know what enzymes are often tested to determine if the blanching process was good? Peroxidase, lipoxygenase. So either peroxidase or lipoxygenase. If they are inactivated, then all other enzymes are inactivated. Okay, other examples for use of enzymes in food, whether in food analysis or in food system. Anything you can think of where enzymes are important, Carol. During fermentation, yes. Sometimes you want those bacteria to grow or yeast to grow to give you your enzymes and to have the fermented food. Okay, but what else? Medora. Exactly, cheese making. So it's a processing aid. Enzymes can be processing aid. So you have your milk, you add rennet or chymosin, it breaks down kappa casein and allows the caseins to interact with each other with calcium bridges, you get your curd. All right, so processing aid. What else we produce with enzymes that is an ingredient in the market? We just gave an example of high fructose corn syrup. What else? Protein hydrolysase. There are ingredients that are used in protein bars, for example, in infant formulas. They hydrolyze the protein and it becomes more biologically available. So processing aid. What did we learn about analysis using enzymes last time? What application?
We use them for like caffeine determination using HPLC with the dairy coffee drink. We use lipase to digest the proteins.
Very good example. I wasn't thinking of that example, but yes, we use pepsin to break down the protein to release caffeine so that we can analyze it. Very good. But recently in carbohydrate, Kevin.
For like
Total dietary fiber, we use a bunch of enzymes, amylases, glucoamylases, proteases, to break down everything and let the fiber sediment. We also determine total starch, break down everything to glucose, measure glucose, and then you get total starch. So let me reveal what I have here. Food quality. So when we are assessing blanching or pasteurization, I gave example. Processing tools, we just gave few examples. Measuring the activity of an enzyme, for example, like in big production facility for cheese, you want to determine how much rennet you need to produce a certain amount of curd in a certain period of time. So you need to learn about the enzyme kinetics. So how much enzyme I'm going to add? I need to know enzyme activity. I need to know the maximum velocity of the enzyme or rate of the reaction. I need to know a lot about the enzyme if I'm going to use them as tools in my process. Or if I want to inactivate them, I need to learn about them in order to be able to inactivate them if I don't want them. Sometimes I inactivate them by thermal treatment. Sometimes I inactivate them by using inhibitors. So I need to measure the activity of the enzymes to assess how much I need of those enzymes, how much I need of an inhibitor to inhibit the enzyme, and so on. Quantification, we gave examples like total dietary fiber or total starch or a measuring of glucose, sulfite. We'll give more examples. Sample preparation, which is important in dietary fiber, where we have to prepare the sample by hydrolyzing everything except dietary fiber. Adding the pepsin, that was a very good example for sample preparation for caffeine. Waste management. Sometimes you have byproducts that you, before you put them down the drain in a big facility, you have potentially fat and protein or carbohydrate. They're going to clog the waste channels. So you put enzymes to clarify your waste so that it doesn't cause clogging of your pipes. So because of all of this, we need to understand enzyme kinetics. So in order to use an enzyme, to inhibit an enzyme, we really need to understand certain characteristics about the enzyme. So I don't know what you covered in food chemistry, but here I'm just going to give you a brief overview of what Km is, what Vmax is, just very brief, what factors impact your enzymatic reaction. So you really need to understand factors that impact enzymatic reaction so that you can understand what it takes to inhibit an enzyme, what it takes to add an enzyme, what does it mean, how much of an enzyme I need for me to be able to determine constituents such as glucose or dietary fiber. Okay. So that's why I'm going to give you a very brief overview of enzymatic reactions. So I know you covered this in food chem. It doesn't hurt to learn a little bit more about it from a food analysis perspective. So enzymes are what? They're catalysts. They're biological catalysts. So basically they reduce the energy required for reaction to move forward. So and what happens when you put an enzyme with the substrate, you form an enzyme substrate complex. So the rate of the formation of ES is K1. That's the rate of the first reaction. So let's say here we are breaking sucrose into glucose and fructose. So the first thing is for the substrate to bind to the enzyme at a very specific location, binding site. Then the kinetic energy needed to move into products is decreased in the presence of enzyme reaction is faster and you need less energy, you break into products. And then the enzyme is released again to be reused. So the enzyme can be reused. So the first reaction is binding to the substrate. You get the ES complex, and then next you have two reactions. This is the non-covalent reaction, so it can go backwards, and it can go forward to produce product. The more substrates you have, the reaction is driven forward. So if you saturate the enzyme with the substrate, then you get more forward and less backward. So velocity of the reaction is important. And where do we measure the velocity of the reaction? So what you see here is a graph that shows the products on the y-axis, and here is the time of the reaction. So when we put the enzyme on the substrate, there are milliseconds that are needed for the enzyme on the substrate to bind. The enzyme substrate bind, then you have what we call steady state. Here you can see it's a little bit linear. So a linear line where you have a steady state, rate of disappearance of ES equal rate of appearance. So this rate of appearance equals rate of disappearance, either into the product or going back. This we call the steady state. The slope is the velocity of the reaction. And we always want to have our reaction in the linear state, because when we quantify, we like linear relationships. So we always work in the linear space where the velocity is the rate of the reaction. And it is the slope of the line is the velocity, or what we call initial velocity. So V0 or initial velocity is basically the slope when we have a steady state. Again, products against time. You get here with time, you get more product. You see here a plateau over time because you deplete all the substrate. You reach a time where no more products are produced. So we don't want to work here. We don't want to do measurements here. We want to measure where it's linear. Okay. Next term I want to introduce is maximum velocity or Vmax, Vm. So here you run the reaction under different substrate concentration. You get the initial velocity for each substrate concentration. And then you plot initial velocity at different substrate concentrations. So here it's showing you the relationship between the substrate and the velocity of the reaction. Okay, if I say plot the relationship between substrate and velocity, this is the plot you draw. So what happens is when you increase the substrate concentration, the speed of the reaction increases. Because when you put more substrate, then you're driving the reaction forward. You're driving the reaction to produce product. So with higher substrate concentration, we get higher velocity until we reach Vmax. At this point, no matter how much we increase the substrate, that's it. You saturated the enzyme. There is no more additional or faster reaction. So you get to a plateau. So here, no matter how much you increase the concentration, you get to a plateau. Here, in this region, is it first order or second order with respect to the substrate? Let's see what you remember from the previous class. In this region, is it the rate of the reaction is first order or zero order with respect to the substrate? In this region.
I'm gonna guess first.
Huh?
I'm gonna guess first.
First, so let's define what we mean by zero versus first order. When we say zero order, that means the velocity is independent of the substrate. That's it. No matter how we increase the substrate concentration, the velocity doesn't change. That's zero order. First order, that means here in this region, the more you increase the substrate, the higher is the velocity. So the velocity of the reaction is dependent on the substrate. So it's first order with respect to the substrate. In this region, it's zero order. Because it plateaus. No matter how much you're increasing the substrate, the rate of the reaction is not changing. Okay. So another term I want to introduce is the Mentalism constant, or Km. What Km is basically concentration of the substrate. Km is concentration of the substrate where you have half Vmax. So Km is the concentration of substrate, where the velocity is halfway between 0 and V. Okay. Why is it important? It's important because it tells me the affinity of the enzyme to the substrate. How much there is affinity for interaction. The higher the affinity, the lower is the Km. Always remember that. It's inverse. The more the enzyme have affinity to substrate, the Km is less. That means at less substrate concentration, you can reach the half maximum velocity with less concentration of the enzyme of the substrate. When Km is high, that means you don't have that much affinity for the substrate. You need much more substrate concentration to reach halfway of Vm. Anything that you'd like to do? So Vmax and Km are important characteristics, kinetic characteristics that we need to know for the enzymes before we use them. Before we use them in a reaction to quantitate or use them as a processing aid, we need to understand their Vmax and Km with respect to the substrate we are using. These are key characteristics for utilizing enzymes. So The Km and the Vmax are both affected by different factors. Importantly, of course, the nature of the enzyme and the substrate, so they have affinity to each other, so they're impacted by that. pH impacts the ionization of the enzyme and ionization of the substrate, so it impacts how well they have affinity for each other. Same as temperature impacts the configuration of the enzyme. And whether or not we have inhibitors. If you have inhibitors, sometimes the affinity to the substrate decreases. If we have inhibitors. Also, the maximum is impacted by the substrate, the concentration of the substrate, the concentration of the enzyme, and environmental factors. So I might ask you, but name 2 or 3 factors that impact one of these, then you would know what to include. Here are the explanations for first order and zero order. When substrate concentration is much, much lower than Km, so we're talking in this region, to visualize that, we're talking in this region, the linear region, much, much lower than Km. The substrate concentration here, much lower than Km. So it's first order with respect to the substrate. As you increase the substrate, you have higher velocity. So linear relationship. So this thing, first order. However, when the concentration of the substrate is way here, keeping the concentration of the enzyme constant, and you're just changing the substrate, then here it becomes zero order to the substrate. So this is what the slide is saying. And this adds to it that when the substrate concentration is way high and you're saturating the enzyme, it becomes first order with respect to the enzyme. So if I want to measure enzyme activity, I want to make sure I have abundance of substrate, a lot of substrate in the reaction. Then if I want to measure the enzyme activity, I want to make sure that as I increase the enzyme, the velocity changes. So I make sure I have abundance of substrate so that not to impede the reaction. The substrate is abundant. We have a zero order with respect to substrate, and I'm trying to measure enzyme. So I would want it to be first order with respect to the enzyme. So this is used to measure enzyme activity, and here you use it to measure substrate. So if I'm measuring glucose, I want to make sure that the substrate concentration, I want to dilute it in a way that it is much, much smaller than Km. Then I can measure my glucose. If I want to measure my peroxidase activity, I want to make sure I have a lot of peroxide. It's not the limiting, the substrate is not limiting. And then the rate of reaction is impacted by the concentration of peroxidase. So therefore, I want to make sure whatever I'm measuring is first order to that. If I'm measuring substrate, I want it to be first order substrate. If I'm measuring enzyme, I want it to be first order with respect to the enzyme. Very important in food analysis. I know you took enzymes in food chemistry, but here I'm putting them in perspective of analysis. That's why I'm trying to remind you what Km means, what Vm means, so that you can put things together. So in order to measure Km and Vmax, it's very important to know these characteristics in order to set up your enzymatic assay. So we can use the Mentalism equation, but it's not a linear relationship. So here it starts linear, it plateaus, and we don't like to work with not linear. So a couple of guys, smart guys, came and said, how about we invert this equation? Let's see what we get when we invert it. So like we invert, these are the two smart people that said, okay, I will invert it. And then now I have a linear line. So the axis is 1 over substrate concentration instead of substrate concentration. And then the y-axis instead of velocity is 1 over velocity. The equation of the line is this, as we call it, Reinberg equation of the line. I don't want you to remember that. You don't have to remember that. But I want you to understand that using this equation, you can get the intercept 1 over Vm, so you can get Vmax. Once you have Vmax, the slope is Km over Vmax. You get the slope of the equation, and you enter Vmax, you get Vm. So now, for every enzyme, if you run the reaction at different substrate concentration and get initial velocities, then you can plot the Reinberg plot and then get the Km and the Vmax of the enzyme. These are essential in order to plan any enzymatic reaction. You need to understand that with respect to the specific substrate and the specific enzyme. Okay, recap questions. I'll skip those. And here we're looking at the impact of enzyme concentration. In this situation, I'm saturating my system with substrate. So I have abundance of substrate, 0 order with respect to the substrate. I'm looking to see what happens to the velocity when I increase enzyme concentration. So you increase enzyme concentration, the velocity increases. However, there's a caveat. You run out of substrate at some point, and you have less products generated because this just depends on how much substrate you have. So here you have 1, 2, 3, 4 lines. Concentration 1 of the enzyme, higher concentration of the enzyme, higher concentration, higher concentration. At time point, let's say 10 minutes. If I use the first concentration of the enzyme and the second concentration of the enzyme, I still have the predicted line pretty much over what actually is happening. So I have that linear relationship. But if I go to a higher concentration of the enzyme, I no longer have the predicted line with the actual measurement. So I have to be very careful in setting up my assay. I don't want to set my assay to be 10 seconds. I cannot control my reaction. I want it to be at least 10 to 20 minutes. So I need to check which enzyme concentration I can work with to get this prediction line similar to what actually experimental it is. So I don't want to go with high enzyme concentration because I will deplete the substrate and I won't have that linear relationship with it. So important things to set up your enzymatic reaction is know what time is good time for you. You want it to be 10 minutes? Can you control it in 10 minutes? Okay, 10 minutes. Okay, and then at 10 minutes, which enzyme concentration would be the best to work with where I have linear prediction line? Another factor that impacts the enzyme velocity or rate of the reaction is temperature. As you increase the temperature, you have higher kinetics. So you increase the movement, you have more faster reaction going on. However, enzymes are proteins. So every enzyme or every protein denatures at a particular temperature. Once the denaturation temperature is reached, you see a steep drop in enzyme activity. So you want to work around optimum temperature, so you will have maximum velocity, but at the same time, you want to be away from the denaturation. So we have increase with temperature to an optimum, to the maximum, and then once the protein is denatured, the enzyme is denatured, and we see a steep drop. Then we have the pH effect. Every protein or enzyme has an optimum pH. It's not always 6. This is the example here. That 6 will have higher activity. Some enzymes like pepsin, optimal activity is pH 2. Trypsin, for example, optimum activity is between 7 and 8. So every enzyme is different. So again, you will have a kind of a bell shape where you have optimum activity at a particular pH, and as you go away from that optimum, you have a reduced reduction in activity. It doesn't matter if you go higher or lower, you just go away from the perfect ionization state. Because at a particular pH, the proteins ionize in a certain way, and that will be optimum for a particular reaction. So one thing you want to note, there is pH stability and pH optimum. So sometimes if you lower the pH down to 3, let's say, the enzyme is still stable, still alive, but it's not optimum pH for it to work. Bring back the pH up, then it can be active again. But some enzymes, if you bring the pH down to 2 or high to 12, they are irreversibly denatured, and you lose the stability and they're no longer active, even if you bring back the pH to the optimum. So that's just an example that while trypsin is not active at pH 3, it's still stable. If you bring it back up to pH 7 or 8, then it will work again. Sometimes you need activators. Sometimes you need some particular functional group that we add, like NAD. Sometimes you need a mineral. Sometimes you need like an iron or an NaCl that would potentially cause the enzyme to be more active. So I'm not going to go into detail, but some are very strongly attached to the protein or the enzyme, and some are not strongly attached. But I'm not going to go over that, but just remember that there are some activators for particular enzymes. Also, there are inhibitors. Some are very strong inhibitors. Some are reversible inhibitors. There are 3 different types. You should have covered those in the camp. The competitive, that means they compete to the same active site. Non-competitive, they bind somewhere else in the protein and change the site where the substrate binds and it cannot bind. And uncompetitive, that means once ES is formed, the inhibitor binds to the ES and the reaction doesn't go forward to products. So just a refresher that there are inhibitors and you should have covered those in food chem. How do we measure activity? Most common, either absorbance or fluorescence. That's most common. So you have a substrate, you have an enzyme, you measure disappearance or appearance of color. That's the easiest, most common way. Whereas manometric method, like measuring difference in pressure, titration, isotope, viscosity, not very common, but they are used. Okay. We talked about coupled reaction before in the carbohydrate acid, Lect. So here we have 2 reactions. The measuring reaction where you have your food constituents, let's say glucose, that you're interested in measuring, reacts in the presence of an enzyme and gives you a product. Sometimes the product here cannot absorb light or fluoresce. Then we take that product, react it with another constituent, then you can get a color formation, or this would be colored, or one of these would be a chromophore, so then you can measure absorption of fluorescence in this case. So that's the indicator reaction, that's the measuring reaction. We need both sometimes to get an estimation of A. Okay, this is called auxiliary reaction as well. We had it in previous slides, but it can also be referred to as measuring reaction. And this is the indicator, that's where color is measured, either absorption or fluorescence. So when we use coupled reaction, we have to make sure that we use enzymes that have similar pH on it. Because if you have one of the reaction requires a pH of 2 and another pH of 8, that's tedious. That's not going to give you error, because you're going to have to adjust the pH, then there is this time difference. That would be an issue. So we select enzymes here that have similar pH optimum, similar temperature optimum so that we have a good reaction. Another thing is the second reaction should not be limited. That means the enzyme velocity here needs to be really high. Otherwise, it would slow down and you might have underestimation. Will slow down your detection and then you'll get underestimation. So these two important factors is the pH selection and that this second reaction should not be limiting. Here's an example of measuring glucose. In this example, we use glucose oxidase. In the presence of oxygen, you get peroxide. Neither peroxide or this product can absorb light. So then we take the peroxide, add a dye. The peroxide is going to oxidize the dye in the presence of peroxidase. So we have glucose oxidase, we have peroxidase. Here, the oxidized dye has color, and then we measure absorption. So this is a perfect example for you to remember. I do not necessarily want you to remember the name of the dye. You can just say reduced dye, oxidized dye. Here's another example for measuring alcohol, ethanol. So in this case, we use alcohol dehydrogenase. You get an aldehyde. You get NADH. This absorbs light, but it has no sensitivity. So we take that NADH and we take the acetaldehyde here, put another enzyme, aldehyde dehydrogenase, dehydrogenase again and produce more NADH. We enhance the sensitivity of the reaction. 2 moles of NADH is equivalent to 1 mole of ethanol. Here in this way, we intensify the signal. We increase the signal by having 2 moles to 1. All right, so examples of measuring substrate. Again, remember, you want it to be first order with respect to the substrate. This is the common question I ask. So substrate concentration much lower than the Km. You have linear relationship. So here you can use it to measure substrate. Sulfite is important in food product and food label because people have sensitivity to sulfite. So you want to make sure if you have any potential of having sulfite in your product, you want to measure it for an indication on the label so that we have an enzyme kit for that. Total glucose, total starch, and D-malic acid is the synthetic form of malic acid. In nature, in apple juice, you have L form of malic acid. If you want to determine authenticity of the apple juice and whether or not they're synthesized versus natural, you can measure the existence of D-malic acid using enzymes. If I want to measure enzyme activity, such as peroxidase, lipoxygenase, to test blanching, we measure sometimes lipoxygenase to determine potential of lipid oxidation over storage. Alpha amylase is important, like in flour, and rennet for cheese making. So these are examples as to when we want to determine the activity of the enzyme to help us either utilize that to inhibit them or utilize them as processing aids or understand the quality of our product. In this case, you want the substrate to be saturated. So you want very high concentration of substrate and much higher than the Km. So you want the reaction to be 0 order with respect to substrate, 1st order with respect to the enzyme. Always you will have standards. In this case, your standards would be enzymes at different concentrations. We have biosensors for, we utilize enzymes, one for glucose. We have the immobilized glucose oxidase, and we can measure the uptake of oxygen. The more you have uptake of oxygen, the more you have glucose. Another one is a sensor for urease, which to detect a pesticide, this pesticide inactivate the urease in insects. So that's why they are pesticides. And then we measure the activity of fluids. If we have the pesticide, the activity will be low. So these are examples. We talked about alkaline phosphatase and measured for pasteurization of milk, rennet activity for utilization of rennet in cheese making, the impact of alpha amylase on the viscosity of flours. We have to inhibit pectin methyl esterase so our pulp remains and not sediment and separate. And when we are blanching. So these are examples for you to remember in case I ask for examples. I have 3 minutes. I want to go back to one thing. I listened to Dr. Dan Gallagher's lecture on minerals. I saw that he did not cover that example calculation in class. What I want you to do, we only have 3 minutes. I'll give you hints, but I want you to do it 4+2 activity for next Monday. We don't have time to spend in class, but this is an important calculation that might show up in the final. So that's why I wanted to go back to it. And I know you guys ran out of time on Wednesday. I can't work like this. I don't know how to open from here. Okay. Ah. You know. Have you thought about it on your own? Because I heard him say you think about it and solve it, and you have this in your slides, but you don't. I don't usually post this. This is after we solve together. I want you to take a picture of this. It's okay to take a picture of this and work on it on your own. Bring it to class with showing your calculations on Monday for +2. And if I have time on Monday, I will go over that with you. All right. Oh, yeah. So did anybody do the +5 for pH and temperature? I see if you did, give them to Nigel. Did you guys collect the protein and fat? You know, you can turn them in anytime between now and end of the semester, all of the extra credit. If you didn't have a chance to do the protein, if you didn't have a chance to do the fat or the pH, anytime. It's almost Christmas. That's my gift. Yeah, so turn it in anytime by next Wednesday, last day of class. All right, you guys. I'll see you on Monday.
Yes.